Okay. Okay. Fire ahead, Sean, whenever you're ready.
Okay, can everyone hear me? Yeah?
Yeah.
Yep.
Okay, great. So thanks for tuning into my talk. And the title is Towards Architecture-Agnostic Neural Knowledge Transfer. And my supervisors are Alessandra Maleo and Kevin McGuinness. So I'm just going to start off for a while talking about neural knowledge transfer in general and what it is. And then later in the presentation, I'll kind of talk about my angle on it, the architecture-agnostic idea. So this is the contents of the talk. First of all, I'm just going to go through a few basics of neural knowledge transfer. Then I'm going to go through a few visualizations that kind of show what's happening. Then I'm going to do a little bit more detail with under the hood. Then I'll talk about the architectural constraints. Then I'll finish with an experimental comparison, just showing some comparison of current methods, and then a conclusion. So neural knowledge transfer is the idea of augmenting the learning process of one neural network with knowledge from another neural network, so another already trained network. And for anyone who's familiar with traditional transfer learning, it's different from that. So instead of copying over the weights, we're not going to do that. We're going to transfer knowledge taken from the activations of the networks when we're passing through a particular data set. So because we're transferring activations taken from hidden layers, the knowledge that we're trying to transfer is intangible, it's uninterpretable, and it's highly distributed knowledge. So it's kind of hard to get a grasp exactly what it is. It's not like logic or something like that. So the benefits of knowledge transfer, why it's worth doing. If you can successfully augment a network with knowledge from somewhere else, you can get faster convergence, which means that your network trains with less training iterations over your data. You can get better generalization, so your network will respond better to new examples, and it won't have as much difficulty with out-of-domain samples. You can achieve solutions with less overall training data, and you can achieve better solutions. So on whatever task it is, whatever neural learning task it is, you can get there with higher accuracies or better scores, basically. So two of the problems that kind of we've observed in the current approaches to neural knowledge transfer is, despite the fact that you're getting around the constraint of having to transfer over the weights, there's still a lot of limitations on when you can and can't use it. I'm going to go into those in detail later on. And there's also no definitive experimental comparison in the literature at the moment. So if you said tomorrow, I want to perform neural knowledge transfer for my particular use case, it's very hard to figure out which method out of the ones that are out there should you use. There is nothing definitive really, or no ranking even that exists currently. So these two problems led us to these two hypotheses. And the first one is more out of necessity than anything. I'll just read it out. Thorough and transparent comparison of existing neural knowledge transfer methods will improve understanding of the challenges and limitations of neural transfer and speed up advances in this area of research. So what we're saying here is that if we can conduct a good comparison of what's already out there, that there should be value to derive out of that, and that should help to better inform whatever comes next, and that we're kind of missing out by not having that type of comparison already. And our second hypothesis is that removing architectural constraints on knowledge transfer methods will facilitate knowledge transfer across a much wider range of tasks and scenarios. So we're just saying here that if we can find ways around these architectural constraints, we'll just be able to use these methods in a whole load of extra use cases, get more value out of them. So all of these methods, I'll talk about them in the context of this teacher-student framework. So this is the idea that we're transferring knowledge from an already trained teacher to a new student that we're training ourselves as part of any use case. And the teacher, we assume it has some kind of desirable properties. So maybe it's got a very large capacity, maybe it's very deep, or maybe it's just been trained on a better data set that we don't have access to, or maybe a different task altogether, but we think that there's value there in the hidden layers or in the decision function that network has learned. So we want to get access to that knowledge on a transfer set and transfer that knowledge through the activations to our student. So just to run through a couple of visualizations that might kind of shed some light, they're kind of like secondary visualizations because you can't directly visualize the knowledge. So we have to use these other ways of looking at the effects of it maybe, or the motivations behind it. So the first one is the idea of attention. So when humans look at an image, they typically tend to focus on the interesting parts of the image, the very salient areas in the image. And so in previous research, someone kind of discovered that the parts of an image that activate very strongly for the filters in convolutional neural networks kind of correspond to human attention when we look at images. So, and this is an example of visualization of that, where the areas that activate the highest are the things like the text on the sign and the faces on the animals, and they're kind of the important parts. So a couple of knowledge transfer methods are trying to focus on this, that maybe attention is the key thing we need to be transferring. And they've shown that averaging all the filters over a particular layer of a convolutional network and transferring that loss is somewhat equivalent to transferring attention. And also people have argued that specific loss functions like maximum mean discrepancy are tailored towards transferring these parts of the images that are particularly salient. Another way that you could visualize knowledge transfer is through the neuron co-activations. So this is the idea that certain neurons will always fire together, and that there's information, there's knowledge contained in these firing patterns. So like, for example, in an image classification task at maybe layer 7, the 5th and the 10th neuron will always fire together, and they'll only fire when they see examples of a car or a sheep. And that's important, and we want to transfer that. So if we have these patterns emerging in both our student and our teacher networks, that we can measure our knowledge transfer by seeing, is there a difference between these co-activation patterns in the teacher network and the student network. So on the image on the left with the baseline, where there's no knowledge transfer, you can see there's a lot of difference in these co-activations for a particular layer. And in the middle, knowledge distillation, which is kind of one of the older methods, you can see that there's a little bit more white in that visualization, so there's a little bit less difference. And then on the one on the right, a more modern method, you can see that they're highly similar. So they've got the same firing patterns, the same co-activations at that layer of the student and teacher. So another way of visualizing the knowledge flow is this idea of knowledge density. So previous research has shown that denser weights lead to better performance overall, and density is measured by the L1 norm of the weights at a particular layer. So it's like an absolute sum of the magnitudes of the weights in a given layer. And when you're training a neural network, naturally, as part of backpropagation, some of the weights will go dead, and some of them will end up with low values. And this is like a problem that they tackle in model compression, where they try and prune out these dead neurons, dead weights. But it's also been shown that if you use neural knowledge transfer, like these kind of methods, you'll naturally increase the size of the weights, and that actually leads to better performance. So the visualization on the right is just showing that even though you'll still have some dead weights, and that's some kind of unavoidable, overall the magnitudes of the weights that are learned in your student network will be bigger than if you hadn't used knowledge transfer. Another way of looking at what's going on, maybe getting a bit of insight into knowledge transfer, is by looking at the example of style transfer, which is kind of analogous to it. So style transfer works by generating a new image and then using two losses: a content loss to transfer the content of an image, and a style loss to transfer the style of an image to a new generated sample. And the style loss that's used here for these examples is a maximum mean discrepancy. And there's 3 different kernels that have been tried out there. So maximum mean discrepancy is also the loss that we use in neural knowledge transfer. But whereas in neural knowledge transfer, we're just transferring directly from a teacher to a student, and there's no option to visualize it. Here, when we're transferring from a target style to a newly generated image, you can actually visualize what's happening. So even though we can't visualize it in the traditional knowledge transfer scenario, this is actually the same information, the very same information that's flowing here in this scenario. It also kind of helps highlight that the different kernels, they transfer different features of the style image, and they're not really comparable. Like, you can't say one is better than the other, but they're all different. So there's definitely different information being transferred with each choice. So then, to go into just a little bit more detail about how neural knowledge transfer works. So all of the methods, all the main methods kind of fit this framework, where you've got 3 steps. Collect activations, where you put in a batch of training data into both your teacher and your student network, and you collect the activations from that data at a certain layer or set of layers. And it's those activations for that training data that forms the basis of the knowledge that's going to be transferred. The second step then is always to perform some kind of transformation on these activations that you've captured. And this is where you kind of encode all your assumptions about maybe what type of knowledge you want to transfer, and you can reshape the data and really introduce assumptions about what you want to transfer. And the last step then is, once you've got your transformed representation of your teachers and students' activations, you align your students' transformed representation to match the teacher's one. So by mimicking this transformed activation form, you're actually transferring the properties of the representation. So you're transferring the knowledge across. So that's the third step. So I'm just going to go through 3 examples of transformations that are common in some of the modern approaches that I've been looking at, just to give an idea of what kind of transformations. So here is the transformation that's used in knowledge distillation, which is kind of the original paper for this line of research for this type of thing. And the key insight here with this transformation is that for a classification task where you're using a softmax on the output layer, the distribution of the output, like on the example on the left with the canteen bottle, it actually encodes information and encodes knowledge. So what's being said here is, because that's the output layer is activated slightly for a mug, well, maybe that encodes the idea that a mug is somewhat similar to a bottle, and also that a keyboard is not at all similar to a bottle. But if you're training with your regular like one-hot encoded training data, where you've got 1 for the correct answer and 0 for everything else, then your training data looks something like the green line on the right-hand side, where you've kind of got knowledge loss, information loss. All you know about is the truth. But if you can collect the output distribution, like on the left, from a strong teacher network, and use that rather than the hard training data, you can train using a signal that's similar to the pink line, which actually encodes that notion that there's some similarity between a bottle and a mug. So. Another transformation is the idea of batch level transformations, or it's also called relational knowledge distillation. So the idea here is that rather than trying to match the representation of an individual data sample across your teacher and your student's network, you should transfer knowledge about the relationship samples have to each other in a batch. So for example, like a pairwise similarity between each sample in a batch might tell you, it gives you a different type of information, more about how they relate to each other. And then you can train your student network so that they should represent that relationship in a similar way, where they relate to each other, rather than directly matching the representation of a single sample across. So it transfers a different type of assumption if you go this way. And the last transformation I'll just show is this idea of the flow of a decision process. So the intuition here is that if you calculate a Gramian matrix between convolutional layers at different stages in the network, this can kind of represent the flow or the relationship between these layers. So if, let's say, you calculate a Gramian matrix between the third layer of your network and the 7th layer of the network, that somehow you're capturing the decision process or the change that happens over that section of the network. And in their paper, they call it an FSP matrix. So if you can calculate a matrix like that over a section of your teacher and then a corresponding matrix over a section of your student, you can train your student to mimic the decision process over that section. So let's say that you want a similar flow to happen over the beginning of your network, maybe the middle and the end. So you can transfer 3 flows rather than directly transferring not representations of samples again. So it's another way of encoding a different type of assumption into your knowledge transfer. So then the final step of the 3-stage process is loss functions. So in general, this kind of fits into one of 2 scenarios, either a joint loss or a pre-training. So when you've got all your transformed representations, let's say you've taken them for 2 or 3 layers, you then want to, you pair them up. So you want to put in place a loss between your teacher and your student at these set of layers. And usually you'll join these losses. So you'll either sum them together or you'll average them out. And then you'll back propagate over the whole student network with this joint loss. And some methods will advocate for including the task loss. So if it's classification, your regular classification loss on the training data, and including that in the joint loss, like the diagram on the left. And some methods will advocate for first doing your joint loss of just your neural knowledge transfer losses first, and then taking that as like an initialization, and then training a second step on just the task loss alone. And there's kind of pros and cons to each, and some methods go one or the other, and some methods can be used in either scenario. So it's kind of, it's an open question, and there's no hard and fast rules over which way to go. And then just to give a really brief look at the types of loss functions that are actually used by methods. So you've got right from simple losses like mean squared error, which is just a regression loss, to people proposing their own losses based off representation learning and maybe even inspired from GANs. So typically the trend here is just to take a loss function from another, a well-developed loss function from some other field with a lot of theory behind it, and use this as justification for your knowledge transfer. Sometimes people will say that they're trying to match distributions and probabilities rather than just matching individual scores and neurons directly. So there's an argument to be made for a lot of different losses, and again, there's a lot of exploration here with different people's methods. A lot of disagreement, I guess. So then to look at some of the architectural constraints that are induced by these methods. So when we say architecture-agnostic neural knowledge transfer, what we really mean is that we want to move towards knowledge transfer methods that work in every scenario, so that they're not heavily affected by differences in the architecture between your teacher and your student. So we want it to work when the teacher maybe is much deeper or has wider layers than the student, or even maybe different activation functions on the layers. And a lot of current approaches have drawbacks here. So what we went and did was to try and kind of categorize some of the main constraints that are prevalent across a lot of methods, and then maybe we can tackle them one by one in the future and design better methods. So a layer selection constraint is the first one. This is just the idea that if you want to transfer knowledge from specific layers of a teacher and student network, you need to actually go in and pick which layers do we transfer from. And it's kind of an arbitrary choice, but it does have a large effect on the overall performance of the method. And really there's nothing there except heuristics very general heuristics about which layer you should be choosing, and there's no reason really why, usually, or even how many losses to apply, or if it's feasible to apply losses, let's say between different stages. So, the middle of your teacher network and towards the end of your student network. There's no way of concretely knowing that, and it still boils down to a very arbitrary choice. And there's no method published that finds any kind of a principled way around this. It always comes down to just a choice. So as a possible way forward to this, we like the idea of parameterized layer selection. So what if you just wired up the whole network to each other, the teacher and the student, or even just sections of the networks to each other, and gave them a parameter that they could learn which losses to activate, which losses to drop, like a gate, possibly. And that way, the network could learn which losses to transfer, and maybe exploit scenarios that we never would have guessed based on our own assumptions, and maybe even activate different losses at different stages. So, like if we see that the lower layers learn quicker at the beginning stages of neural learning, and then towards the end, the higher level, more abstract features learn later. So maybe if we had a parameterized knowledge transfer, we might see a similar phenomenon where knowledge flows early in the lower layers, and knowledge might flow more in the higher layers later in training. The second constraint, and this is definitely the most troublesome constraint when it comes to actually using these methods in practice, is the idea that you can't transfer knowledge from layers that are not the same dimensions in your student and your teacher network. So it's a massive drawback, really, because it's rare that two networks will have the exact same architecture and the layers will happen to be the exact same. And you need to be able to tailor the network for whatever the architecture of the network for whatever task is at hand, and even to fit the dimensions of your training data as well. So because it's such a prevalent problem, people have been looking at workarounds for this already, and typically these methods are applied with image classification and almost all of the convolutional neural networks. So people have just looked at altering the architecture of the student to match. So doing things like interpolating filters and max pooling operations, just to basically force the architecture of the network to fit the size of its teacher. And another way of getting around this is with an intermediate regressor. So this is just placing an extra layer on top of the target student layer, which fits the size of the teacher, and then training that as normal with the knowledge transfer, and then discarding your intermediate layer at the end. And this kind of amounts to like a random projection into a higher or lower feature space. So there's going to be information lost here. It's less than optimal. It's been shown in other papers. So what we think would be better solutions moving forward for layer size constraints is the idea I talked about earlier with batch level transformations. So you can actually just engineer your way around the problem altogether this way. So if you, for example, if you calculated pairwise similarities between the samples in a batch, and you had, let's say, 10 samples in a batch, then you'll end up with a 10 by 10 matrix representation at the end of that. And if you do that in the student and the teacher with a different layer size, you'll end up with 10 by 10 matrices. So you've actually avoided that problem of dimensionality having to match. But if that wasn't possible, another interesting avenue which hasn't been explored would be the idea of just better layer resizings as opposed to intermediate layers. So the diagram on the left is from a paper where they show that you can increase the width of a layer and preserve the original function. And this was in a paper where they just wanted to increase capacity of networks so they could continue training them. But I don't think there's any reason why we couldn't use this approach for knowledge transfer, just to get around the idea of not being able to transfer losses between layers that don't match in the size. And the final constraint I'll mention is the need to retain the teacher's original data set for knowledge transfer. So this, like for example, will come up in knowledge distillation because it works on the output layer of the network. So you absolutely need the original training set for this to work. Most methods that focus on the hidden layers can get around this. But if this is a problem with a particular method, one workaround that has been shown to work is to synthesize a fake data set from statistics taken from your original data set. So if you can capture the average and the standard deviation of activations for every layer in the network, you can reverse engineer a data set and transfer knowledge with almost as good as you would have done with the original data set. So then to take a look at experimental comparison of a couple of methods. So this is the experimental comparison that we conducted as part of this research. We took five representative current approaches and evaluated in a model compression scenario. So what we mean here is we're transferring knowledge from a large, powerful teacher network to a smaller, less powerful network on the same task. So we're not changing task, we're not changing domain. It's just 63% shallower and with 68% less parameters. And we want to measure the increases in performance on a classification task in top 1 accuracy. And what we observed here was that knowledge distillation, which is kind of the older method, outperformed a lot of the newer ones. So this was a surprise to us because in most of the original papers, they'll claim to beat knowledge distillation. And we also observed that sometimes knowledge distillation will be improved if you combine it with other methods. Because knowledge distillation works on the output layer and the rest of them work on hidden layers, they lend themselves to being combined. And we also have kind of evidence to believe that some of the least architecture-agnostic methods actually perform the best. So, for example, knowledge distillation and FSP, they're both carry a lot of constraints on the layer sizes, and it's very hard to find scenarios where you can where you can use them. So they're not very agnostic, but yet when you can use them, they seem to perform well. And I'm just going to mention this comparison as well, which is from a paper I just read last week, a new paper from ICLR, and it's the most comprehensive comparison of present methods. And on the top line is the results for knowledge distillation, and they actually found the same conclusion we found, was that the original knowledge distillation outperforms a lot of the newer methods that have came since. So that's the green and red arrows are the ones that have surpassed knowledge distillation, and almost none of them can actually do that. And it also highlights just the slim margins overall between these approaches. So even though a lot of them are very different in the way they work, they're still very 2 and 3% is all the improvement you'll get on a task like this, which is image classification on CFAR 100. And just a conclusion. So what we think would be the ingredients for a high-performing architecture-agnostic knowledge transfer method would be to use batch-level transformations where you can to avoid the idea of the layer size constraint. And if you can't do that, then to investigate using function-preserving layer sizes as opposed to random projections as a way around. That we should select a loss function with a strong theoretical underpinning, so maybe a loss function that has a good basis in representation learning, and that we should explore parameterized layer selection to avoid the human in the loop trying to pick out which layers you should be transferring knowledge from, and to automate the process a lot more. And the research tasks for us in the remainder of this research is to build out our experimental comparison. So what we had there was knowledge transfer on the same task from a high capacity network to a low capacity. But obviously we want to investigate knowledge transfer across where the teacher was trained on a different task or trained on data from a different domain. And we want to investigate new metrics that go beyond just the task specific metric, because we don't have any particular metric for knowledge transfer itself. We're always evaluating in terms of performance on whatever task we're using it on. We want to propose a new knowledge transfer method based on what we've identified as being the key ingredients, just what I talked about in the slide before. And finally, off the back of our comparison, where we see that sometimes the least agnostic methods perform really well, we want to kind of investigate that a bit more and see, is it always the case where there's a trade-off between an architecture-agnostic method, which can work in a lot of scenarios, and achieving high performance on specific tasks? And if that trade-off does exist, does it exist equally so for every task? Okay, thank you. That's finished.
Okay, thanks a million, Sean. Very good. So I'm now going to hand you to, well, we're going to take some questions from the audience. If anybody wants to ask any questions, please do. Anybody? Any questions from anybody? I will
Can I ask a question here to get the ball rolling?
That's great.
And so you're evaluating there in terms of using a very domain-specific measure, a top one accuracy. Yeah. Is the, let's say, the pattern of accuracy similar if you were to use top 5 or other measures as well? I suppose I'm trying to ask just to get a sense. There's nothing idiosyncratic about that particular measure using top 1, where another measure might reflect a different pattern of results in terms of what's increased or what's not.
For image classification, I haven't seen anybody use anything, top 5 on any of these papers. So I guess that hasn't been checked. It's always top 1 accuracy they use for image classification, and I haven't checked myself either. So
another question I have as well: when you're evaluating for the CIFAR data sets for the 10 and the 100, when using these various different approaches, obviously you're seeing an overall increase in accuracy, but are those increases in accuracy maybe restricted, let's say, to certain labels that, like you're saying, oh, it's able to detect these, I don't know, 20 labels out of 100 more effectively, but the rest of those other labels, nothing's being transferred or nothing's improved about their accuracy? And I know that's something you mightn't have looked at. It's more just a curiosity on my side.
Yeah, no, that it would be interesting, all right, but I haven't looked at that myself either, and I haven't seen anybody else look at that in any other papers, so can't speak to that really.
Okay, yeah, it'd be more just a curiosity of what's actually being transferred or whether it gives some insight. Another question I have, and then I'll hand back to the floor. You're using pre-trained networks in all cases when you're doing transfer learning. So you're using a pre-trained ResNet 101 or something like that on the CIFAR data set, or are you training both of these in tandem together? So